Hello, my name is Mohammad Sadri. I am a postdoctoral researcher at TU Kaiserslautern, Germany, and this is another video of the videos that I am creating regarding designing embedded systems with a ZYNQ device. Yet this video is another hobby video, I will call it, and it's just an screencast. But as you will see soon, we are creating a set of videos using a professional studio, and those videos are not mine, of course. They are TU Kaiserslautern videos, but I will add the links to those videos also here on my own website. So today I am going to talk in more detail about AXI stream interfaces, and I want to go a little bit inside to see what are the signals used in an AXI stream interface and how do they interact, how two modules with AXI stream interfaces talk to each other, and how you can design your own custom AXI stream interfaces. Towards this, I use the Vivado HLS tool to create some sample modules, and these modules will contain AXI stream interfaces. I go through the whole flow from the C code, then to the synthesis, to packaging the IP, and then to using the created IP inside the Vivado environment itself. So I will show you as an example case how you can use the C language and the Vivado HLS flow to create your own modules with AXI stream interfaces. The goal is to show the AXI stream interface. The goal here obviously is not to describe how you develop your hardware using the C language in HLS. That is another topic, maybe we will cover later. Then after that, in another video, I will focus on developing AXI stream interfaces and modules containing these AXI stream blocks using pure RTL. So we suppose that there is no HLS flow, and we use pure RTL to develop these interfaces. So what we do in this video is that we use the Vivado HLS and we develop some example units. We go for each example unit through the whole flow. We develop a test bench for the example unit inside Vivado HLS, and using the test bench we look at the waveforms and how this module operates. The three example modules that I have considered for today's video are these three. The first one is just a simple counter. It counts continuously with the incoming clock, and it contains one AXI master stream interface, which is basically showing the counted values. Then I extend the functionality of our simple counter to have another port through which I can load to the counter up to which value you should count. After that, we develop a simple module which basically receives some values, some data over the GPIO interface, over the general purpose IO interface, and puts those values on its own AXI master stream interface. For this example, the GPIO in will be an stream of input bits. So basically we have a serial to parallel converter, or I would say a shift register. Okay, let's go and start with Vivado HLS. Here I have the command prompt in which I can issue the Vivado HLS command. So first I create a folder. For example, I create a folder, I call it ZYNQ session 06, and I go inside and I directly call Vivado HLS. If you're not using a server and you're not in the university, or you don't have an administrator, you are the administrator of your system yourself, then before issuing the Vivado HLS command, obviously you need to source the file which contains the related configurations for running Vivado and Vivado HLS. So for example, it would be a command like source, for example, software, or source opt. Usually in personal computers it is opt, but here in my case it is software. And then you have the ZYNQ folder, and then usually inside the ZYNQ folder you have Vivado, and then inside Vivado you have the version that you want to use, and then you have in fact the file that you should source. Obviously based on the shell that you are using, either you are using bash or you are using CSH or whatever shell you are using, you should source suitable settings file. For my case, I should source settings 64.csh. And now my system is ready to run the Vivado HLS. And for this to come up, we need to wait a little bit, maybe and now I go ahead with create new project. This is kind of old version of Vivado HLS that I have here on this system. The concepts that I am showing today are exactly the same for newer versions. So in newer versions you will have things more than what I am showing to you here, but these concepts are exactly the same. So I will call it simple AXI stream counter. Oh, I removed the simple, just AXI stream counter. And top function, I will use exactly the same name, AXI stream counter. And I don't want for now to set any flag, and for the device, in fact for the FPGA, for the part on which you want to implement this system and you want to synthesize your module for that part, I come to boards, and for now I select the Z board. I press OK. Now we have the Z board here. You can define also a target clock frequency for the module that you are designing. So, but I think for now 10 nanoseconds meaning that your module is going to run at 100 megahertz, I think it's completely enough. So I go ahead, press the finish button, and we have our project structure created. Okay, what should I do now is I should write the simple C source code for the counter, and for that I prefer to use an external editor. Okay, so I have the lovely Kate here, and inside Kate I begin writing the code of the counter. Before that, maybe I can try to increase the size of the fonts that we have here. Okay. So edit, probably settings, configure Kate, and fonts and colors, and just I want to make it slightly bigger. Yeah. So I begin writing the C source code. This is Sadri, and this is a simple AXI stream counter. And now the C source code, so it would be something like this: int AXI stream counter, and my AXI stream counter needs an AXI stream output. So I would say int counter output, and this is the definition of, in fact, the ports and the interfaces of my module. And then inside the module, obviously I need the registers which are counting themselves. So I would say static int counter value, and it should be defined as static, and it's better for me to also initialize this in the beginning to a fixed predefined value. It is static because in fact every time that I want to call this function, every time that this hardware is going to run, is going to execute its own related task, then it should begin from its previous state. In fact, in every clock cycle that this hardware is called, is executed, is run to do its task, and the task is counting, it should count from the previous value. So I define this as static, and then what I do is simple. I define a variable, or even I don't need to define a variable. Every time I increase the value of the counter by 1, and what I do, I write this value at every cycle to the output. And then here the function, I have defined an int as its return value. So for now, let's always return 0. Okay, this is our code, and ZYNQ session 06, and in this folder, ZYNQ session 06, which is our project folder, I create another folder. I'll call it C, and inside the C I store this file. I will call it AXI stream counter.c. And one good suggestion is that don't store your file with the C extension, always store them with C++ extension, because as far as I have seen, Vivado HLS is sensitive to this extension, and later when you want to use certain structures inside your HLS code, then due to this sensitivity, Vivado HLS will not allow you to use them. So I think that CPP is a better choice, definitely. So I come here, I go to the C folder, and just I change the name of my file to CPP, and then I come back to Vivado HLS environment and right click on the source, add files, and I add in fact the C source code that I have written just now. Here is my C source code inside the Vivado HLS environment. Okay, we have the C source code here, and for this C source code, what I want to do, I want to tell Vivado HLS that this counter out interface, I want it to be an AXI stream master interface. So what I do, as you open your code inside Vivado HLS environment, your code will be analyzed on the fly, and the important structures, important elements of your code will be listed on the small window beside the code. And here on this window, if you come to the directive part, you come to the Directive Tab. Inside the Directive Tab, you have the list of your interfaces. In fact, the input outputs of your function, which are practically the interfaces of your final RTL module. And this counter output here, I can select, I can right click, insert directive, and then I insert a directive, in fact a compiler directive, a hint for the compiler, for the synthesizer, about this interface. The hint that I am going to add is that the interface of this port, this variable, the interface of this variable, I want it to be an AXI stream interface, and I press OK. As you do this, you had a new statement appearing here, and also if I look here at solution 1 constraints and directives.tcl, I can see, if it opens the file, I can see that a directive is set here which is saying that the mode of counter output, which is an interface inside AXI stream counter, the mode is AXI stream. And this is completely enough for the Vivado HLS environment to understand that you want this interface to be an AXI stream interface. That is it. Our code is ready. We go ahead and synthesize our code and see if there is any errors or there is any problems that we should solve. Okay, as soon as the synthesis gets finished, you receive a kind of report about your module, the important parameters of the synthesized design. For example, the device. As you see, I selected the Z board as the device for our project. So you see here the ZYNQ 7020 device here, and then there's a kind of timing report for the design that we have created, and then there is the interval report and latency report of the HLS module that you have created, meaning that when you insert the data into the module, the latency, insert the data into the module, how long does it take, how many cycles does it take for the output to appear, and then each processing, each execution task for each new data, how many cycles does it take. Well, the Vivado HLS document describes these parameters in detail, and if you don't know them, I invite you to read the document directly. Then there are some other, in fact, informations provided in this document, such as resource consumption for this module, and then there are the rest of the information, such as ports that you have inside your module. And now if I look at my project structure, we have the synth folder here, and inside the synth folder you can see the outputs of the synthesis that I have done. So I ran the synthesis, and here are the outputs. And in fact, what Vivado HLS performs for you, it gets the HLS design, and for you it creates the equivalent system C, the equivalent Verilog, and the equivalent VHDL of the code. And for now, since I love Verilog, I open the equivalent Verilog of the code, and what I want to show you here are the list of the ports inside the Verilog module that is created by Vivado HLS. What you see here is in fact one AXI stream master interface, which contains practically 3 ports: the T data, the T valid, and T ready. T data, T valid, they are output ports, and T ready is input port. And then you see some other ports which Vivado HLS adds to every block that it synthesizes automatically and by default. You can disable these inter-block communication signals, but usually it is a very good idea to keep them there. Here we have the clock and reset. They are normal clock and reset inputs that every module has. And then we have the start signal, through which you can control if this module is going to be enabled, is going to be operating, or it should be disabled. It should not do anything. Then you have the down and idle and ready signals, which are practically showing if the task that we have given the module to do is down or not, if the module is in idle mode, and if it is ready to accept a new data. So these signals can be very useful when you have several units developed in HLS and you want to connect them and you want to allow them to talk to each other. But at the same time, if you have just one unit of this type inside your design, again these ports can be useful, because through these ports you can control the module completely and evaluate its status. Either it is finished the task or the task is still running, and when can I issue a new data to the module, and so on. Okay. But our focus is practically these 3 guys here, since they are the AXI stream interface. Now I go ahead for my design, and I create the packaged IP out of this design so that I can include this IP inside another project in Vivado environment. Previously, I pressed this button to synthesize the design, and now I am pressing this button to create the packaged IP, and I am for now jumping this button through which I can perform a simulation on my design. At the next step, we will come here and we will evaluate this one. So export RTL, and Vivado asks me what kind of output do you want me to generate for you. I want just a simple packaged IP that I can later include it inside the Vivado environment. So I press OK. While our packaged IP is being generated, let's develop a simple test bench for our module. Okay, the packaged IP is being generated. I will later show you how we include it inside Vivado. For now, I go ahead and I create a simple test bench for my AXI stream counter. So I have AXI stream counter. This is the module, and I come back to the Kate. I create a folder. I call it SimC. I go to SimC. I run Kate, the editor. And here I begin writing my test bench. So Sadri, this is a test bench for AXI stream counter. And before I begin the test bench code itself, I include a declaration for the function that I'm going to test. So the function that I'm going to test is AXI stream counter. It contains an integer output as the return value of this function, and then it contains one integer pointer as its input. So this is the first line of my test bench, and then I go ahead and I say int main. So your test bench is your main function. The test bench in Vivado HLS is always the main. So I have the main, and what I want to do inside the main, I want to execute this task, the task that AXI stream counter is doing. How do I do that? I simply call this unit, this module. And by calling this module, in fact, I am simulating the operation of enabling this module and making it to do the task that we want for every clock cycle. So how do I write my code here? I first define a simple integer, int I, and then I create a for loop. Let's say the for loop is counting up to 100, and then inside this for loop I will call my unit. So AXI stream counter, and then I need to in fact read the output of this unit and store it in a variable. So int, for example, y, and then here I pass to my unit the address of y, and for the main the Vivado HLS checks the output of the main function when it performs simulation. If the output is 0, it means that the simulation is executed fine and the outputs of this function is matching the outputs that we generate ourselves through the test bench. If the return value was non-zero, then Vivado HLS understands that the test bench, the test operation, has not been gone as we have expecting, and it stops the simulation with an error message. So for now, I don't intend to compare the outputs of this unit with any other reference. So I want just to see them, and I directly return 0. So this is our test bench, and practically in terms of hardware, what is happening is that for every clock cycle we are asking this unit to do its operation. For every clock cycle we are asking its unit to count. Okay. So this is my test bench. I go back to the Vivado HLS environment, and I add the test bench here to the test bench section, add file, and here system C, and I don't know with which extension I have stored this file. Maybe I have stored it in a yeah. So let me copy paste this file and save it. Save AXI stream counter test bench .c pp. Okay, and I save it. I come back to Vivado HLS and I add the file here. This is what I want. Okay, now this file is also added here, and then later we can use this file to do the simulation. But before that, I want to show you the output of this stage. We press this button and we created the packaged IP, and I want to see how I can include and use the created packaged IP inside the Vivado environment. So I come to my command prompt, I come out of here, I create a Vivado folder, I go to the Vivado folder and I run the Vivado environment directly. Okay, we need to wait for a while. Yeah, so here I have Vivado environment and I create a new project. Yeah, not important. Okay, let's keep everything as it is. I just go ahead until I reach the board section, and in this section I select the Z board, I press finish. Okay, we have the environment, and at the first point we add the repository in which we are keeping the created packaged IP inside HLS to this project. So I come to Tools and Project Settings, and inside Project Settings I come to IP and I say Add Repository, and then I will be provided hopefully with a dialog box that I can use to select the address to the repository. Yeah, so this is the dialog box, and here as the repository that I want to add, I indicate the AXI stream counter. This is the folder that contains my Vivado HLS project. I just select it, and as you add this here, you will see that in the IP in selected repository you have the AXI stream counter added. Okay, and you press maybe apply, and then you press OK, and then now I can look at my IP catalog inside the project and see if the IP block is really added to the project. If we scroll down here, we have Vivado HLS IP, and inside the Vivado HLS IP it is our block AXI stream counter. And now I create a block design. For now design 1 is fine. And here I can add my, in fact, AXI stream counter. AXI stream counter. So this is our block. As you see, our block has its own clock reset input, AP control. These are the signals that I briefly described to you, through which you can control the operation of your unit. And then you have the counter output, which is practically an AXI stream interface output, and I can connect it to other modules. So for example, if I include another AXI stream unit here to the story, I can connect this guy to that other AXI stream interface. Let's try it. So I would say AXI stream, I don't know, yeah, let's try the floating point. I don't know if it's a good decision. Sorry. Yeah, so I have this guy here, floating point, and then I want this output, the output of my AXI stream counter, to be one of the inputs of floating point. Okay, although the numbers that I am producing here are not floating point, they are 32 bits integer numbers, but in AXI, in HLS environment, I could define also the output, the interface of my unit as floating point, and then this was completely making sense to connect this port to this port. And then inside the floating point you can in fact define what kind of floating point operation you want to do, and then you can very easily and fast have your desired floating point calculation being done inside Vivado environment. The point is, in practice I may never do that, since the floating point operation that you want to do here I can also do in one line of code inside my C code in Vivado HLS environment, and this connection is just an example. Anyway, I come back to Vivado HLS. I have added the test bench to the project, and what I want to do, I want to simulate the operation of this unit. the operation of my counter unit. So I go ahead and I press this button here, run CRTL co-simulation, and it's asking me the blah blah blah, and I say yes. It's not important, just go ahead. So blah blah blah. Okay, yeah, then the dialog box appears, through which you can select which simulator you want to use for this simulation task. You have complete list of simulators available in the world, and for now I keep it as auto. And then here you can select either you want the Verilog RTL, VHDL RTL, or System C design to be practically simulated. These three are, in terms of functionality, they are equivalent, and there's no difference which one you select. And if I select Verilog or VHDL, then I need to in fact run a simulator, because for simulating Verilog or VHDL you need one of these simulators here. But if I select the System C, then as you know, System C is C. It gets compiled, it becomes an ELF, the ELF gets executed, and you have the result. So practically you don't need a simulator. So I keep it as simulator, but what I do here is in options part I select dump trace, because I want to see all of the traces, all of the signals inside the design. And I press OK, and we wait again slightly for a short amount of time. Okay, I think the simulation is done, and if you look at the log of the simulation, you can see that in fact the traces of the simulation, they are all stored as a VCD file, and we can directly open that VCD file. So I come to my command prompt, I come out of the Vivado folder, and I go to AXI stream counter, and inside AXI stream counter solution 1, obviously I go to sim folder, and inside sim folder I go to System C folder, and here in System C folder you find a set of VCD files that are the outputs of your simulation. You can open the VCD file using GTK Wave, which is free, or if you have license for any of those simulation tools, you can use them for opening the VCD file. For now I use the DVE, the Synopsys VCS, for viewing the VCD file that I want. So DVE, this master here, yeah. I'm not sure if I have for DVE, I'm not sure if the system is set up. Just one moment, I need to set up the system for DVE. Sorry. Yeah. Okay, I have the DVE here, and DVE is the waveform viewer of Synopsys. Obviously it is very powerful, and it's a part of VCS. VCS is also very powerful, and I really like it. And now I do open database, and I just go ahead and open the VCD file that we have, and then I add these guys to the wave. And inside the wave we have in fact the operation of our module, And let's for now focus on our AXI stream interface, which is here: T ready, T valid, and T data. And you obviously see your counter is counting. Yes, it's 12, then I would say 13 and 14, 15, and it's not a big deal. It's very simple. And you have, in fact, the T ready is driven by your test bench, and T valid and T data are the outputs of the module that we have developed. And this is a kind of art of Vivado HLS. It generates for you all of the unnecessary, I would say, less important interface signals. So as you see, for example, is also driving automatically for you the IP underline star, which is the signal which controls the enable disable operation of your module. So it really facilitates your simulation and verification task. Okay, now I go ahead and I create a slightly more complicated design in which I add one AXI slave stream interface to my code. So I have AXI stream counter. I have AXI stream counter, which is here inside the C folder. AXI stream counter. This one is wrong. AXI stream counter .cpp. This is the file. I just copy, paste this file into a new location, and I add range word here, and I add an input. The input that every time it indicates up to which number I want to count. So I would say int count range. And what is the operation that we want to do right now? Every time that a count range is loaded into our module, we want to begin counting from 0 to count range. And then we do the same operation for the next count range. So I have counter value, and the point is, this time I don't need it to be static, because I receive the execution task, I do the execution task, I finish it, and then later I receive a new one. So it's int counter value, and what I want to do is that we have a kind of for loop. So int I, and or maybe the counter value can play the role of I, so I don't need I would say for counter value equal to 0, counter value smaller than count range, and counter value each time it will be increased by 1. And let me make this window slightly larger, and each time what is happening is that the counter output is driven by counter value. So this is our code. Every time that it is called or it is executed, it performs one complete set of count operations from 0 to the value indicated by count range. And let's save this code. So I will call it AXI stream counter range.cpp, and inside the C folder I'm storing this file. And I go ahead, I come back to the HLS environment, I say I want a new project, I will lose the current project, that is okay. The name would be AXI stream counter range, and top function is the device for the project, boards, Z board, yeah, finish. And I have already developed the code, so add files, C AXI stream counter range, and for this unit that we have here, AXI stream counter range, what I do, I define both of the ports as AXI stream ports, and Vivado automatically understand that this one is an input, this one is an output port. So here, directive count range, insert directive, and I define this as an AXI S. Yeah, counter output, insert directive, and I define this again as an AXI S. Yeah, so we have the design ready, we can develop a test bench for it. So let's do it also right now. I have my function, I come back to Kate, I create a new file, test bench for AXI stream counter range, and this is the declaration of the function that we want to test. And okay, so int main void and int I, and for I again the same story I am keeping repeating. And let's have also the y value, and I call this method AXI stream counter range, and as the input I give the I itself. So the first time I want it to count to 0, the next time I want to count it to 1, then 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on. And here as the output I give all of the outputs to y, and intentionally I return 0, and I finish the test bench. So the test bench should be stored in SymC folder, AXI stream counter range test bench.cpp, enter, and this is the file. And I come back to the Vivado environment, and also I add this file, add files, and to the SimC, and is this one will be added to the project. And let's go ahead and synthesize the design. So synthesize. Okay. Okay, this is ready, and the point here is that since then you don't know anything about the latency and interval that takes the operation to be done. Why? Because it really depends on the input itself. So based on the input, this value will change. Anyway, I go ahead and I perform the simulation directly. So I come here, I press this button, System C, dump trace, and OK. Let's see if things goes fine or there is any error somewhere. Okay, now the simulation is done, and I come back to the DVE environment, and let's see if inside DVE environment we can see the, so this window I don't need, this is the previous simulation. I close it and I open a new database. So open database, and this time the database is located somewhere else. So the database this time is inside the AXI stream counter range. AXI stream counter range, solution 1, sim, and inside the system C folder I should have my VCD outputs. And I think, yeah, I can select this one, the main one, and yeah, the file is getting opened, and let's see what we have here. So add to wave. Okay, first look, some red lines, and red lines means problem. Yeah, red lines mean problem usually. Okay, anyway, let's see what has happened. Now we have the count range port here, and then we have those signals which are not important. I would like also to see the count output which is not inside this Vcg trace. Anyway, for now we can look at the behavior of count range port, and what I want to show here is that this slave port, because count range is a slave port for our test bench. In fact, as you see, this slave port, look at how T-ready is changing. T-ready is no more always 1. Yes, it gets 1 in just some specific situations. I mean, as soon as one counting task gets finished, it gets 1, and another task will be issued to the unit, and then it goes to 0, meaning that I can no more accept any new data for now until I finish the counting task. And okay, so practically what is happening here is that the T-ready is driven by the module that we have developed, and T-valid and T-data we are driving. The test bench is driving them. And if you look at T-data, obviously it is sometimes red, meaning that the value is not specified. It is obvious because we are not always indicating this value to the but then in some locations you can see it has values. So yeah, so first time is 0. We are commanding the module count to 0. We are commanding count to 1, count to 2, then count to 3, count to 4, count to 5, and as you see the distance is increasing because each counting task is taking more time. Count to 6 and blah blah blah. EF 11, 12, 13 and so on. Okay, now let me try to open a more complete Vcg trace. Here is, I don't know if, yes, this one is, I think this one makes more sense. Okay, let me, because I want to, so we have, what do we have here? We have also the counter output port. We have the counter output port and we have the count range port. Both of the ports we have here, and the rest of the signals, they are not important to me. Only these two guys, they are important. And here I think we see a clear behavior of our module. Let's have a look at counter output T data. This counter output T data is the output port of the AXI master stream port of our module on which it is counting. So what I expect to see, I expect to see an output like this: 0, 0, 1, 0, 1, 2, 0, 1, 2, 3 and so on. Okay, so let's have a look. What do we see? 0, 1, 0, 1, 2. This one is not important because at the time of this value being generated on the output of the module, the T value is 0, meaning that the next module that is going to receive this data, it will receive this value, it will receive this value, but not this value, because T value is not 1. And the next module, which is connected to this module, will only receive data when T value is 1. So 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on. So that our module, our units are kind of operating. And briefly, if we want to tell everything, the T value is indicating if the data which is now residing on T data is valid or not. Whenever the data is valid, T valid is 1, meaning that the next module can grab the data. Whenever T valid is 0, it means that the data on the output is not valid and the next module cannot grab the data. Then we have the T ready. The T ready means that this port is able to accept new data. Here T ready of the counter output port is not important because this T ready is driven by our test bench. Is not important, is always 0. But as I showed you, the T ready here has some parts in which it is 0, because actually the count range port is not ready to accept any new data practically from the test bench for now. Okay, so the T ready indicates if your module is able to receive new data. The T valid indicates if the data on the output port is valid, and T data contains the data counts themselves. Finally, let's inside the Vivado HLS environment have a look at the generated RTL for this module. So I come to the Verilog folder and I open this file here. and we have the module, I would say block-to-block communication interface, or the control interface that Vivado inserts inside the design automatically. And then we have the signals related to our AXI interfaces, and I go down. For the signals, we see that the count range data is input, obviously, because the count range is an AXI slave port. So T data is input for count range, T valid is input, and T ready is output. For the other port, which is counter output, the T data is output, the T valid is output, and T ready is obviously input. Okay, now I go toward my final example, and the final example, we are creating a kind of GPIO to AXI stream converter. As you have seen, the AXI stream is very simple. Even you can directly code it in RTL, and you don't need to really deal with coding with HLS. It's not that complicated. But anyway, as I have showed you, using HLS, you can really accelerate your design. Okay, for final part of this video, and the final example that I want to show you, I go ahead and I try to write the code. So, and we don't evaluate it, I just write the code. So, and I hope I do it correctly. Sadly, simple GPIO to AXI stream converter. Okay, and int AXI stream GPIO, and here I put the GPIO which is entering my module, and here I want to use the structures of the data structures provided by Vivado. So if I recall correctly, API int, and for now I want an input port of 1 bit width. So it's just a stream of data coming into my module, and then I have input data as the port. The other one I keep it as it was, output date. Okay, I go ahead and I say static int bit counter. We need a bit counter to count every 32 bits, because practically we want to gather every 32 bits and then to put the resulted paralleled 32 bits value on the output data. So we have the bit counter, and yeah, this guy is beginning from 0, so I have an initial value for this method, and then probably I need another variable which is keeping the intermediate value of output data, obviously, and that one static int temp maybe output. I define such a value, and I say whenever a new input data, new bit is entering our system, what we do, in fact, we add this bit to temp output. Okay, so what will happen is that temp output is equal to temp output multiplied by 2 plus input date. And at the same time I will have bit counter increased. So this is what happening by every clock cycle. The point is we check the value of bit counter and if one complete 32 bits data is now received and ready, what we do is that we put this value to our output. So I would say output data is equal to temp output. And I need to put back the bit counter to 0 and to put back the temp output also to 0. And what else? I think we can finish the code. So I will call this one AXI stream GPIO.cpp, and this time the .cpp is extremely important. Otherwise you will have problem with this guy here. Okay, I think this is the code. I come back to HLS environment. I hope I have not made any mistake. I don't know. We will see. I make a new project. Okay, AXI stream GPIO top function AXI stream GPIO. The device board and the Z board, and we finish. Okay, the folder structure, and to the sources I add file. Here C and AXI stream GPIO. And let's open it and see if there are any problems and try to solve the problems. Probably I need to, I'm not sure. Yes, I need to include, I think, include one header file here. I think, yeah, so I need to find what is, yeah, let me close the DVE. And have a look at the code. Yeah, happy int, I think things are fine. Okay, I will try just to Yeah, okay. I couldn't make it. I don't know what is the problem. Yeah. So I would say I am sorry. I don't know what's the problem. I don't know. I don't have right now any idea. AXI, yeah, okay. This is the problem. Probably we have misspelling the name of the function. Let's try again. Yes, it is done. Just I come back. So as you see, the synthesis is done completely, no problem, but still the interface of Vivado is showing me that there's a problem here. There's no problem here. There was a problem here until we were not adding this header file, but as we added the header file, there's no problem here in this definition. What I want to do, I come to directive, and as previous step that we had, I defined output data as one AXI stream interface. So interface, I have AXI S, and for input data I define this interface as a kind of interface which contains the valid signal. Okay, so is input data and interface, and I want to be API valid, meaning that in fact with input data, along with input data also we have a signal which indicates if the input data is valid or is not valid. And I will synthesize this master again. Okay, it is done, and I come here, solution 1. I look inside the synth folder. I bring up the generated Verilog code for this block, and the Verilog code for this block contains signals, 3 types of signals. I would say the general control signals related to the module, then it contains the signals related to my general purpose input, which contains in fact the signal himself, the input stream of data, the signal himself, which is 1-bit signal, and another 1-bit signal which is indicating if this input is valid or is not valid. I mean, at each clock cycle, is this a valid value or is not a valid value? This is important, and this is because of the type of interface that we define. And then we have our AXI stream output interface, and then I can go ahead and package this IP. So I package this IP, Okay, and now I want to include the package IP here. So for now I delete these guys here, and I make it slightly bigger. I come to tools, options, tools, project settings, IP, add repository, yes, and inside add repository I select the AXI stream GPIO, and I close it, and here I select AXI stream GPIO, I add it, and now I have it. Yeah, and now what I do, I want to use this module. It's practical, it's a kind of useful module. It's kind of receiving data from output and putting them on the AXI stream interface. And suppose that here this is the block that I have, and I want to create a kind of more complete design. So suppose that I have also a microblaze core here, microblaze. And this master microblaze, I configure it and I tell it to have AXI stream slave interface. This is one interesting capability of microblaze, which can have directly AXI stream interfaces. So let's go ahead and see where is the configuration related to AXI interfaces, and I want microblaze to have enable microblaze to blah blah, enable local memory bus, AXI interfaces, select bus interface, number of stream links. Okay, what do I have here? AXI enable instruction, enable number of stream links, stream interfaces. I want one AXI stream interface, and yeah, I don't like it. This is very limited. The configuration should be much more extended, and I think I was checking other versions of Vivado and it is much more complete. Okay, I changed it to advanced, and here buses, I have one stream interface. I cannot configure anything else, just let's go ahead. Yeah, now what I have here is one AXI slave interface, and I can connect the output of my kind of serializer, deserializer to this AXI slave interface. And for the microblaze, of course, I can run block automation to make it operational and working, kind of. So I want it to have local memory. I don't need any ECC. I don't need the caches. AXI interconnect should be there, and yeah. So I just press OK. And I finalized the design by, in fact, focusing on our module. Suppose that the data is coming from outside, so I select this guy here and I create an interface port out of this guy. Or suppose that these are driven by a GPIO module. It's a more general case, so I have an AXI GPIO. The AXI GPIO is here, and the output port of the GPIO is in fact driving this signal here, and on the other side the slave port of GPIO is connected to the microblaze. So what is practically happening right now is that we have the microblaze, and the microblaze is able to access the AXI GPIO through its memory mapped interface. So we have the memory mapped interface of microblaze, and as we see, AXI GPIO in address editor will appear in the address range of the microblaze. So in your C code, which is running inside microblaze, you can access this module, you can write to this module, and practically what happens, the content that you write to this module will appear on this port and will enter our in fact AXI stream GPIO interface, and the output of this guy is an AXI stream. So practically what we are creating right now is a simple method that we convert the AXI memory mapped interface to AXI stream interface. Of course, there are much better methods, much more efficient methods, but you can inside the HLS you can increase the width of this guy to whatever value you want, and also you can drive this port with maybe another GPIO module if you want, or you can tie it to one, and then you have the conversion from AXI memory map to AXI stream directly. Okay, so maybe I can double click on AXI GPIO, and I don't know if I can have GPIO width. It will be all outputs. For now the width is just 1 bit, and I want to have 2 GPIOs, all outputs 1 bit, and OK. I press OK. GPIO 0 and or GPIO 1, GPIO 2, and I want in fact to connect this master to here. Okay, so I am driving through GPIO both of the ports, so I can transfer data effectively to this module. And for the clock, I connect this clock to the clock that I think is already added to the system, the clock that is driving the microblaze CPU core. They are the same entity, so I connect this clock here. And for the reset, probably I can use also the reset that we have here for the microblaze. So I go ahead and I connect these two together. Honestly speaking, right now I don't know the reset that we have for the microblaze is active low, active high. I don't know that. I think the reset that we have here should be active high, and this one seems to be active high as well, but this should be double checked, and if needed a kind of NOT gate should be added here in the path of this port. And then in AP control In order for this module to operate, I want to keep the module always active, so I just tie the AP start to a constant value. I come here, I say add IP, and I type constant. We have a constant value, and I connect the constant value that I have here to AP start, and for the constant value I double click and I say that I want the constant value to be always 1, is always 1. Okay, I regenerate the structure that we have created, and now our structure contains the microblaze CPU core, the GPIO. Practically we have created a very simple AXI memory mapped to AXI stream interface. The design that we have right now doesn't make sense at all, because you come out of microblaze and you go back to the microblaze itself. But it's just a design, it's just an example. Here we use the AXI slave stream slave interface of microblaze, and you may be wondering how a microprocessor can have a slave port. The answer is it cannot. And what is happening practically here is that you put the data, and the microblaze whenever wants he fetches the data. So I would say a kind of register buffer here to which you write, and you cannot write anymore until the microblaze fetches data that you have written. Okay, and then yeah, I think for now we have a kind of design which is almost complete, and I don't know if it is working or not. It's not currently important. For the clock input, suppose that the clock input for now is coming from outside, so create port, and I have the clock port entering the clock wizard coming from outside. So on your board you have a clock generator. This guy comes from outside, and yeah, so I don't know why it didn't connect these two guys together. So I connect this one here. Oh yeah, that's a differential clock. That's a differential clock. So yes, this is why it didn't do that. It's a differential clock. So I create an interface port. Yeah, sorry, it is not a normal clock, it's a differential clock. And then we have the reset here. This one is port, so create port, reset. Okay, and I regenerate the structure. It's a kind of structure, it's just an example. Okay, so up to this point we use the Vivado HLS and we design some AXI stream interfaces. I would like to thank Professor Luca Benini of University of Bologna and ETH Zurich and Professor Norbert Bain of TU Kaiserslautern because of their support. Without their support, these videos would never have come into existence. These videos are hobbies, they are not official. They are my own personal view of designing with Vivado and designing for the ZYNQ device. I may have mistakes, and this doesn't in any way have any relationship with any university or anyone. These are just my own personal views. And for latest material related to these courses, please refer to my websites, thegreenelectrons.com and googlia.com. Both of them are my own personal websites. Thanks for watching. See you in the next video, in which I will dedicate the time to designing the same thing using pure RTL design. Thanks. Bye.